Integration techniques, lesson 3, derivatives of inverse trigonometric functions. Inverse functions. Given a function f(x), the inverse is often expressed as f to the negative 1x. Relate this to basic operations. For instance, the multiplicative inverse of 4 is written as 4 to the negative 1, which in turn can be written as 1/4 or 1 over 4. Linking this to f(x), the inverse of f(x) or f to the negative 1x could be expressed as 1 over fx. Derivatives of inverse functions. To find the derivatives of these functions, we will use this result. dy dx equals 1 over dx dy. If you think about it, if you divide by dx dy, you end up with dy dx. The following proof examines the derivative of inverse tan x, or arctan x. Let y equal inverse tan of x. Rearrange, make x the subject. Now differentiate. Dx dy equals 1 over cos squared y, which is sec squared y. Take the reciprocal of both sides. Now apply the trig identity to your denominator. Sec squared y equals 1 plus tan squared y. So replace sec squared y with that. Given x equals tan y, we can now replace tan squared y with x squared. So dy dx equals 1 over 1 plus x squared. Similar proofs can be explored for the derivatives of inverse sine and inverse cos x. The derivative of inverse tan x over a equals a over a squared plus x squared. X is any real number. Here, you just got a little proof. In terms of your general function, if it was, just think if you had inverse tan of just x, a value would be 1. Hence that would be a 1, and that would be a 1. But because you've got a function here which x could be divided by a, or its multiple of 1 over a, you're then going to divide by that derivative, which is 1 over a. And if you expand that, you end up with the a over a squared plus x squared. Example 10. Differentiate inverse tan of x on 4. So let's differentiate d dx of inverse tan x on 4. A value is 4, so it's 4 over 4 squared plus x squared, which is 4 on 16 plus x squared. The derivative of inverse sine x, or sine x, inverse sine x on a, is 1 on the square root of a squared take x squared. Differentiate 5 sine, the inverse sine of 2x on 5. Now, I'm going to write that. Dx of 5 sines the negative 1 of x on 5 is 5 lots of, because that 5 is just the multiple of that inverse sine function. 1 on our a value, which is 5 squared take x squared, which is 5 on square root of 25 take x squared. Derivative of inverse cos, or arccos, is negative 1 over the square root of a squared take x squared. So differentiate arccos of 1 take 4x. Here you've got a composite function, so let u equal 1 take 4x. So now you have y equals the inverse cos of u. U dx equals negative 4. Apply the chain rule. So the derivative of inverse cos would be negative 1 over the square root of a squared take x squared. But that x here has a u. So negative 1 over the square root of a squared take u squared times by du dx, which is the negative 4. Now a, in this case, is 1. Here, dy dx equals 4 over 1 squared take 1 take 4x squared, because u was 1 take 4x. Hence, just by expanding, completing your perfect square, you can simplify that as 4 over the square root of 8x take 16x squared. Just think if you multiplied negative 4x by negative 4x, you would have your 16x squared, but that's a subtraction sign. you'd have your 1 times your 1, hence the 1 take the 1 is going to be 0. Then you've got negative 4x times 1 double that, which is negative 8x, but take negative 8x will become the positive 8x. That's the end of our derivatives of inverse trig functions.